Okay. So, yesterday we have looked at the purpose for which these offshore structures are designed and constructed. Today what we are going to see is specifically offshore structures fixed to the seabed. That means, we are not going to look at the floating systems, we will look at the fixed floating fixed platforms for the purpose of exploration in shallow water. While doing so, we will just look at what other things is available both for fixed and floating, but in detail we are going to just look at the configuration of the system. So, the structures can be classified into bottom fixed structures, means the structures are fabricated and installed and fixed to the ground by pile foundations or other forms of foundations. So, you have jacket or template type structures, compliant structures. We will see the difference between what is the idea behind jacket structures and compliant towers. The second class will be floating structures, where the load transfer is by means of buoyancy. So, there is no foundation except for mooring lines. Then the third is gravity based structures. So, you can see there the load transfer and the resistance is coming from the weight of the structure. The first one, basically the most commonly used structures for shallow water. The third category, the gravity based platforms, also used in shallow water as well slightly deeper water depths, but for very deep waters you normally go for floating structures. Among there you got 3 or 4 categories, which we will see in little bit more detail one by one. I do not think you need to write down, as long as you can listen here, you can read the notes later on I am going to give you. So, the 3 classes: bottom fixed structures, floating, and then resting on ground. So, resting on seabed, 3 classes. So, you can see easily distinguish 3 categories, basically how the load transfer from superstructure to substructure, substructure to ground or to the seabed or to the foundation. So, basically that is how. So, we will be focusing on in this course the bottom fixed structures and especially the jacket or template type structures to the great extent. I think one by one we are going to see some pictures as well, understand the concept of how the load transfer is happening. Fixed platforms, compliant tower, both are based on fixed to the ground type. Then the remainder is almost all of them are floating type, one by one we will go through, and the last one is the gravity platform. So, if you see the history of platform development, you could see that gradually as the exploration extends towards deep water, you could see from a shallow water jacket to a slightly deeper water jacket. Is actually, if you see the first one and the second one, this does not work. Basically the jacket is slant, you see the difference, the face is slant here, whereas the jacket face is made vertical. The reason behind, if you make the similar design, for example, the shallow water to deep water, the base of the jacket becomes too big. Typically, if you look at a 100 meter water depth, 1 in 10 inclination of the legs. We will see why we are doing this later part. If you do the same thing here, what will happen? The base becomes too large. With today's installation capability, it will be too big for transportation and installation. So, basically that is why you made it slender, then we do the remedy by means of other specific design. Basically, it becomes too slender, almost a cylinder cantilever, whereas the first one becomes better in terms of bottom fixity and the displacements will be controlled. So, what we need to see is what difference it makes in terms of operational capability, because we made it cylinder, and how do we remedy that situation, because we can't build a platform of a similar kind, becomes too big, number 1, too big in the sense too costly, number 2, and installation may become a little bit problem. Of course, in the recent past, like within last 20 years, 600 meters water depth jacket has been installed in Gulf of Mexico. So, how did they do it to overcome the installation is a different scenario. So, the third one you see, as the water depth increasing, we have shifted to a concept where structures will be floating, no more fixed to the ground, because basically the making of a similar structure in a very deep water becomes impossible, or it may be too expensive, and come up with an alternative solution. Basically the total load transfer is happening by buoyancy. So, basic idea is the gravity loads are taken by buoyancy provided by the hull, the floating system, and the station keeping is done by several means. One of the idea is here mooring lines going vertical. We do not normally call it mooring lines, we call it tethers. Basic idea is they do not spread, they go vertically down, and all the time these lines will be under tension because you have a excess buoyancy. So, when you tie them to the ground, always under high tension. So, that is called tension leg platform. Basically there is no leg except that you got tethers vertically moved to the ground. That means there could be potentially a design of foundation required there, because you got to fix the mooring lines or the tethers to the ground. A similar concept, but exactly the hull shape and dimensions are slightly different, but other than that the idea behind is similar. You can see the tethers going down vertically, which is called a mini TLP, which is just a variation of the conventional TLP with the pontoon at the bottom. Here also pontoon at the bottom, except but only thing is instead of 4 column stabilization, here you have a single column stabilization, basically little bit weaker, but here you got the legs are spread over larger dimension. So, the stability could be better. So, you see this the evolution of various configurations over the period of time. If you remember, if you go back 1960s or 70s, even building a jacket of this kind was so difficult, because those days capability of machineries and availability of equipments were not so much, but 70s and 80s started to build up bigger and bigger jackets, reached the highest of 600-700 meter water depth. But then after 80s, many of these floating solutions have come up, which means depending on time of the availability and the technology available those days, even building a jacket would have been a very big challenge. 1970s building a jacket in 100 meter water depth is a big worry, but today building a jacket in 100 meter water depth is a simple exercise. Many of the contractors can do it, whereas building a TLP or other types of floating systems even today is a big challenge, because the systems have been continuously changing. So, the other form of hulls which also gives you an idea of change in concept, instead of very shallow draft hulls like what you saw from the previous picture, something like this, you see here the deep draft hulls, we call it DDF, deep draft floaters, vertical cylinder floating upright with a specific means of design. You could see this hull also been moved vertically sometimes, or slant lines, either taut or slack, but you could see that the stability is coming from single leg. So, how do we stabilize? When we go for a design, very easy. Basically the large mass at the top makes the system very unstable. So, what you need to make sure is center of buoyancy is always up compared to center of gravity. If you have otherwise, what will happen? Immediately capsize. Whereas, when you go back to the previous system, you see here stability is automatically achieved because the legs are spread and waterline area is smaller and waterline dimensions are larger. So, waterline area is smaller, the dimensions are very large, whereas when you come to this hull, both are same and it is only a single mono hull. That is the biggest problem. So, design of spar, you need to make sure that the center of gravity and center of buoyancy is aligned properly. Always center of buoyancy should be at the top, so that it becomes upright. And similarly, you have various other hull forms like the one FPSO systems, conventionally used by means of simple tankers, but sometimes we have a special hulls, something like what you see in this picture, but very rarely. Most of the FPSOs are conversion of existing old tankers and retrofit. So, how do we do it? Basically is the hull design for each of the location, which location, which type of hull is suitable, first needs to be selected. For example, if you go to a cyclone prone area, the FPSO hull is no good, because the load attracted by the hull will be very large. That means designing mooring systems could be potentially proved to be very difficult. Whereas, if you go for a calm places some of the Gulf area, you could see that the loads on the hull will be very small. So, you could actually have a spread mooring. So, spread mooring versus the other type of mooring or station keeping system needs to be arrived at based on the environmental conditions. Over the period of time, various types of floating hulls you could see, some of them are like a semi submersible. We will see what is the meaning of semi submersible. Basically, idea is the hull has the vertical columns as well as the bottom pontoons submerged below water with a reasonable excess buoyancy, and the spar, the extended drilling platform, very similar to semi sub, except that the bottom is having another deck for supporting some of the equipments, and a typical floating production and storage and offloading. Basically, this is a very good concept developed around 1980s, where marginal fields are, yesterday we discussed about marginal field, where pipelines are very expensive, the location is very far. In such cases, what you need is produce and store, and the oil tankers, shuttle tankers will come and offload and then transport to land. So, you need a temporary storage, that means you need to have a storage tank. So, this type of ships will have chambers, you can store the produced oil and later on transfer to the cargo ships or cargo tankers, which can transfer the cargo to the land. So, that is the idea behind, and mostly the FPSOs originally developed for marginal field, but nowadays it has been used for other conventional field, because instead of storage you directly have a pipeline transferring the fluid to the land. One of the greatest advantage of FPSO is it is relocatable, reusable, and in case if this field is exhausted, you could actually disconnect and go to another project or another field with simple modification to the topside equipments. You may not exactly use it 100%, but at least you can relocate the hull, relocate the equipments without spending too much of money, whereas the fixed platforms, the relocation actually becomes costlier than the installation itself. You will get that type of numbers when you actually ask for removal. They will charge you more than the original cost of installation, because most of the work involves subsea cutting, removal and relifting, and once you assemble such a big platform from small pieces of equipment, getting them into smaller pieces for easy of lifting or transfer becomes really expensive. That is why most of the platform after the expiry of their life still actually lying there idle, many of the locations. As per the recent regulations, you are supposed to remove the platforms, that aged platforms beyond their service life, you are supposed to remove, because they should not create problem to the environment. Many of the countries like European countries, they have mandatory regulations, while installation you should have provisions to remove, so that the next time when you are trying to remove, it becomes easier than nowadays we do not have any such provision. So, a fixed platform means we got several components. I think as I explained yesterday, we have a superstructure like any other infrastructure facility. You have a superstructure housing most of the facilities that produces oil and gas, support systems like living facility, power producing facility, and then the flaring facility of exhaust gas, and you have a substructure which is made of primarily steel frame, which you could see a typical tower, and most of the time we have a tower made of tubular members. We will see the reason why we do that. Then the tubular structure is arranged and organized in such a way that the base is larger and the top is smaller. It is a very simple common sense. You could see that the base is larger, your inertia of the structure will be better or increased. If you make a parallel bracing or parallel column, you will have a reduced base, which will make reduced strength against horizontal loads at least. So, basically most of the structures will be of this kind with pile foundation, mostly steel tubular piles fixed to the ground and fixed to the structure. So, we need to see how it is integrated. We have a foundation, we have a steel structure needs to be connected to the ground by means of pile driving. Most of the platforms built all around the globe are less than 500, except few exceptional cases, and very commonly you see that in this part of the world both from Chinese oil field to Middle East, most of the platforms are less than 150 meter. You do not see any platform except in two locations where we have done 200 meters in Chinese waters. Otherwise, most of the platform less than 100, 150. So, you will see that most of the activities in this part of the world, we are talking about almost shallow water. There is not much deep water projects, except if you go to Gulf of Mexico or North Sea or elsewhere, you will find even jackets go up to 500 meters water depth and beyond. Nowadays, the new projects, nobody is going for even for 500 meters jacket projects, because for 500 you got a better solution using floating systems. But 1970s and 80s, even for 500, floating systems were not able to be designed. So, they were looking for fixed structures, but now more than 200 meters, every one of them is floating systems, because they become economical and easy to manipulate. And you can see that structures have several configurations. Later on, when you refer various references or textbooks, you will find that various configurations could be found, like 3 legs, 4 legs, depending on the design requirement, depending on the floor area, and depending on this environmental conditions. For example, you have a 100 meter water depth, you put one single column, typically will be able to design what type of diameter is required. All of you might have studied your simple mechanics, Euler buckling, most of you have studied hopefully. So, if you look at the diameter versus length ratio, you could easily find that for 100 meters you may need a larger diameter single pipe, is not it. But if you put 4 columns, probably you could reduce, because the flexural strength will increase because 4 columns are there. But if you have a braced tower, something like this, you could also see the diameter can come down to as much as 1 meter or less. So, the idea behind from single column to 3 column, 4 column or 6 column or 8 column is just to reduce the diameter. But why? Because the larger the diameter, fabrication becomes too difficult, number 1. Number 2, even if you have a 25 meter diameter, 100 meter long, you still will have a sensitivity against the dynamics. Later we will study in one of the course why slender non-redundant structures are not good for dynamic loading, because its potential proved to be dynamic excitation. So, that is why we have such a history of redundant structures with many lattice frame arranged together, so that though it is going to behave like a cantilever, but at least have a spread over a larger area, or the dimension at the base is bigger. And most of the time we use 4 or 8, 3 or 6 is very uncommon. Sometimes, very rarely we use. Most of the time we have a 4 leg, typically like a tower. You might see, like many towers on land. You go to transmission tower, or you look at a water tank tower, mostly 4 legs. 3 legs, one of the potential problem with 3 legs is its asymmetry against loading. 4 legs, at least you get a symmetry in 4 directions, asymmetry in diagonal directions, but 3 legs you get everywhere asymmetry, and the directional dependent loading could potentially prove to be a disaster. So, that is why normally we do not use it. Of course, 8 legs is better, again will be similar to 4 legs, but then depends on the floor area requirement. If the area required for process platform is larger, then you go for a 8 leg. If the area required is smaller, you go for a similar, like a simple building design. If you have a building, your floor area required is only just 20 feet by 20 feet, no reason to go for 8 columns, because 20 feet any RC column or RC beam can actually span, and design is easy. But if you need 100 feet, then probably you need series of columns. It is exactly the idea that we just, but it is not that simple as what I have just explained, because there are other parameters will come and play. Even if it is say 20 meter, 30 meter, depending on the method of installation, you may actually change the number of legs from 4 to 8, depending on whether it is a launch method or a lift method. So, there are various things that will come and play a role in selection of the geometry. And the last one need to be a little bit understand this idea, what is called a natural period. Most of you have some knowledge of dynamics in your BTech course, at least the primary structural dynamics? Not so much. Anyway, the structural dynamics is definitely an integral part of offshore systems, without which you can't design. The idea behind is, when you have a structure too slender, the oscillation, I think you can go to, maybe in the first semester you may be having a laboratory. I think one of the lab they will be teaching you how to do a free vibration analysis or free vibration testing. You know, if the structure is too slender, you will see that the oscillating period will be small or large. So, basically the idea behind the stiffness versus the oscillation. So, if you look at most of the structures around 100 meters, 150 meters, the oscillating period is around 1 to 3 or 3 to 4 seconds, within that kind of. So, that is why this is very advantageous, because they are away from most of the sea waves that you can see many parts of the world. You know, if you go around, sea waves have a period of 4 seconds up to say 16 seconds, but never ever come less than 4 seconds. Very rarely you get a small wave of 3-second period. So, it is a very good advantage that we are away from the resonance going to happen if you have the wave period and the structural vibrating period is very close. So, once you know these two subjects, then you can speak more. So, let us not go into that right now, because you will be doing this dynamics course in this semester, I think, or next semester. So, once you get into the dynamics of the system, then you will realize the importance of this number. But historically it is proven that most of the structures have the period, because it is bottom fixed and have pile foundation to the ground, and it is a frame structure. You will find that most of the vibrating period is less than 4 seconds. But if you take a similar system, go to a floating system, you will see that the periods could be as large as 20 seconds, 30 seconds, 40 seconds. So, you either have there or here, you do not come into lock in period of 4 to 16, it is very good, is not it. So, that is the idea behind. We will see in the last slide how people have designed over the period of last 30-40 years, either below 4 seconds or beyond 20 seconds, which is away from the next one is the compliant tower. I think you understood the idea behind the fixed platform. Then we go to the fixed platform with a slender structural arrangement. That means the structure is purposely made slender, because the water depth is here is too large, that if you make it large base at the bottom, becomes potentially expensive, difficult to install. And then sometimes we have the guy wires fixed to the ground, but that concept has not been utilized so far in the real field, except in very few locations, because of the vulnerability of the cable to break. If the cable breaks, what happens? The system becomes unstable, and that is why very few locations so called guide tower has been used. Otherwise, it is designed as a compliant tower. So, what is the meaning of compliant? Basically, when the wave forces act on the structure, it is not going to resist as a rigid structure, it is going to get displaced. So, there is a relative motion between the wave and the structure, allowing the large bending. What we do is we have a little bit of relief from the loading coming from the waves, number one. But then how do we sustain that motion here? We change the equipments at the top to suit such a large displacement from the sea waves. So, that means there is a certain price to be paid, because not all equipments will work. Typical example will be a drilling system. You expected a rigid platform for drilling. Now, this platform has a large displacement horizontally, typically about a meter or so. So, means those drilling systems or the equipments needs to be modified in such a way that they will be able to operate, otherwise they will fail terribly. So, this compliant tower is basically a simple idea that suited well for those time when the water depth were larger, when the floating systems were not possible, and we went for this type of system. But nowadays nobody is going for compliant tower, because we got very good floating systems available for the design when the water depth is more. That is why if you go into the literature, you will not find many of these systems used in the past, only very few, if you count maybe 5 or 6 of them. So, and the natural period is very large, because of the slenderness, it just goes beyond the wave. So, that is how you assign the structural strength in such a way that you do not go into a lock-in period of say 10 seconds, 15 seconds, it becomes a potential problem. Resonance will be creating a lot of trouble. So, here the manipulation of the structural system is done in such a way that the period is going beyond those 20 seconds. Sometimes we use the tuned mass dampers in such a way that it go you beyond there. So, manipulation of the structural arrangement could be made because it is very cylinder, and the mass system at the top would make the larger the mass at the top, you will see the period shifting higher and higher. We have seen this earlier, tension leg platform. The concept is very simple, is very similar to a simple floating pontoon. The load or the payload is at the top and it is floating because you have excess buoyancy. So, you may see that if you look at that, there is a horizontal pontoon. Pontoon is connected to 4 legs, and each of the columns is connected to the ground by means of tethers. Many occasions in the literature you will find tethers are mooring wires, typical mooring wires, but in recent cases we actually have structural members, tubes, large diameter tubes attached to the hull as well as to the ground, which gives you little bit of horizontal stiffness also, and at the same time you have a positive buoyancy which creates always tension at the hull there, the line or tether line. So, this is a variation of the second one is basically a mini TLP, which is very similar function. So, the load balancing for both of them is weight is smaller, buoyancy is larger, and larger the buoyancy, more will be the tension in the tether lines. So, basically that is the idea behind, and horizontal stability is achieved by means of the tether movement. Basically there will be always be a delta movement horizontally, because you do not have a inclined mooring lines, all of them are held vertical, and this is very good for drilling, because the most of the problem for drilling is the vertical movement. As you can see, heave movement is going to be a bigger problem. So, for example, drilling in TLP based platforms could be potentially very easy, because the heave movement will be very much restrained. That is why you will see that new last 20 years of development for deep water drilling mostly based on TLP concepts. This is another one developed by as early as 1960s and 70s, but never used. This concept is very interesting. Basically hinge at the bottom with a gravity base or piled base, but the vertical column as such is fully buoyant. So, you have a weight at the top. As soon as the horizontal loads due to this wave forces attacked by the external forces to the column gets displaced, but because the buoyancy is available from this column, the buoyancy will bring back the column to the vertical position, to our neutral position. So, back and forth it will be achieved by the inherent buoyancy of the system, but one of the problem of construction is making such a universal joint at the bottom, and it is only in the paper. So far nobody have implemented this, because it is so difficult to construct such a system with a large diameter. You could see universal ball joint in many of the mechanical applications, but they are all very small. You will see that fabricating and installing such a system will be very difficult. So, this articulated tower concept is very interesting, but practically not feasible because of the construction difficulty and normally not used. And we have seen the spar platform. I think there will be one picture. So, this spar concept is very common nowadays, especially in deep water developments, and what you can see here, over the period of time various types of spar, but the concept is similar, is vertical cylinder with buoyancy sufficient enough to hold the weight at the top and to float vertically upright. This is a very important idea. So, how do we do this? We have a top weight and we have a buoyancy chamber which produces or gives us sufficient buoyancy, and also we have a weight at the bottom which we call it ballast, so that the center of gravity is below and center of buoyancy is above. So, idea must be very simple, so that it floats upright. But imagine if you take the same cylinder with no weight, you just put it in water, what will happen? It will float horizontally, isn't it? So, we are just trying to manipulate this buoyancy and the weight so that it comes into this position. Once it comes into this position, then sufficient number of moorings to station keep is a simple system. So, the spar you can see variety of variations, truss spar, cell spar, instead of single diameter single cylinder, you have multiple cylinders of same diameter or different diameters. Truss spar, basically the buoyancy is at the top, but the remainder part is made of jacket, sometimes we call it jacket spar. You have a jacket at the bottom which is hanging from the floating hull and the top sides. The reason why we need this bottom part is basically to support the risers and conductors, otherwise they will be too wobbly. So, you do not want to stop too early, because the wave action in this area could potentially prove to be a problem for the risers. So, that is why you need to support them. So, various configurations, but the concept is very simple. Here buoyancy also must be higher than the weight, and center of gravity and center of buoyancy is manipulated to give a vertical upright position and single column. So, that is the most important aspect. So, the stability is purely by means of manipulation of buoyancy center and center of gravity, whereas the multiple columns, even if the center of gravity is higher, you will be able to achieve the stability like a ship or like other semi subs or 4 column structures. So, this spar in the recent times is getting popular because of its simplicity and ease of installation, and cost efficiency is very high compared to other hulls, and many times in the last 20 years almost hundreds of spar platforms have been installed in the deeper waters. In some cases we also have alternatives. Whenever the water depth is too large and prove to be expensive to go for a floating system, we come with the subsea systems. Subsea system is very simple. Basically you drill the well, but then you do not have any structure. Basically the well is connected from the deep water location to a shallow water location. The similar concept which we have designed for Reliance back in 2004, 2002 times, the water depth is 1200. So, when the design contract was given to us, we came up with an idea that the deep water at that time, even 2002 time, was expensive to go for floating systems, and basically the well was drilled and capped at the seabed. The lines were connected to a shallow water around 150 meter. So, all the wells were connected in a shallow water platform. So, this subsea system, what is the difficulty is capping the well at the seabed at such a water depth, you need a special equipment. That is where you get little bit troubled, because those equipments cannot be supplied by everybody, only very few companies have the subsea system. So, that is when it is limited to few companies doing these projects, but this is proved to be very economical, because you do not need any fixture structure or floating structure in deep water. You will see that well configuration one of the days. And then we have this floating systems, conventional production system or floating production and storage and offloading. Either way, when you have this, you do not have the storage facility, it is directly going through a riser and pipelines, whereas this FPSO means you have production as well storage and then offloading intermittently to a tanker. This is very common even now for marginal field, whereas for full fledged long duration fields you still have FPSO, but we call it FPS because there is no storage and offloading, direct transfer by risers and pipelines. Something like this, you have a FPSO, sometimes you have a loading buoy. So, whenever the tanker is full with crude after producing for a period of time, you bring an oil tanker, transfer through, and then the oil tanker will take the oil away. So, there is no direct lines connected. So, you see here the subsea, the one that we were talking about, many of the wells are connected to one of the floating systems. So, you could see that if you look at each of the solution, you can actually combine any one with any one of the combination, depending on situation, cost involved and the environmental conditions at the site. The reason why we did not go for this for East Coast is because it is cyclone prone area. FPSO's station keeping could prove to be potentially difficult. Of course, can design, but then larger cost. Instead, if you connect all these lines to a shallow water by pipelines and make a fixed structure, it could potentially be cheaper. I think we have seen this spar based concepts. So, all of you, I think what you need to understand is how the thinking has evolved over the time, because constantly trying to improve ideas, so that it two things in mind, not only cost, it is safe number 1, and number 2 easy to install is the second. Third is the economical consideration, because you could have cheaper solution, but cannot install, will become a potential problem. And then the FPSO of different kind, you can see here have a mooring which makes the ship to rotate about its center of the axis. You see here there is a yellow color bearing line, basically we call it a turret, which revolves the ship is going to revolve around this bearings at the center. So, that means this is almost like a compliant system, it is a weather van, we call it weather van, because whenever there is a wave or wind load on the system is going to, the hull is going to revolve around. That means the load is not going to be attracted by the mooring lines. The mooring lines are only going to carry the buoyancy system, whatever the buoyancy available, it is going to just keep it some amount of movement, but otherwise it is only station keeping the inner turret, but the hull itself is not being held in position by the mooring lines itself, because it is weather vanning. So, the only problem with this system is if there is a connectivity between the seabed to the ship, for example, you have a riser typically transferring oil from produced this FPSO, and if it has to go through this and then go to the land. Now, this connection between this line to the ship, because the ship is rotating, imagine it is not a fixed part. So, you have one line coming, but it needs to have a swivel. So, that line also needs to rotate all the time, otherwise what will happen? It will just break. So, that is one of the difficulty where designing a rotatable and leak proof connection between a pipeline coming from seabed to the ship is a big challenge. And of course, it is not something new, it has been in use for several decades. People have designed multiple couplers where it will be able to rotate, at the same time no leakage come through. So, we have several companies supplying such kind of mechanical components. So, that is one difficulty. The second difficulty is designing a bearing system by which the whole ship can rotate. It is not such a small bearing like what you see in motors. So, it is going to be the diameter of that bearing could potentially be 20-25 meters. So, you could see a large diameter bearing by which it could revolve around. So, this has become very common in the FPSO, because you do not have a mooring line problem, because mooring lines are not taking any load here. But this you see at the center of the ship, you have made a big opening, is not it? Normally this is not very good, weakening the ship by sufficient to fail. So, this normally adapted for new build FPSOs. If it is a old tankers converted, you see here we normally do not break at the center. This is actually a old tanker converted into a FPSO, and there we put the similar turret at the tail end, so that you do not need to actually do a lot of modification to the hull, because otherwise it becomes a big project. So, the difference between this and this is the location of the turret. So, the meaning of turret is holding the ship at particular location, at the same time relieving the load by allowing the rotation of the ship about its axis of the turret. You got the idea, simple idea, no? So, this is internal turret, this is called external turret, because the turret is located at the one end, or most of the time will be in the stern end. Sometime you can see slightly inside also, instead of exactly outside, you could also see at the slightly few different cartoon pictures of various ideas, FPSOs. Sometimes you have a riser of this kind, spar drilling platform, extended drilling platform similar to semi submersible, and then this is also a drilling system from one of the companies, DPS 2000. So, this is the picture we wanted to show before we complete the lecture today. Basically, you see here the frequency of the wind spectrum and the frequency distribution of wave, and you see most of the fixed structures actually I should have drawn in period instead of frequency, it would have been easier. So, if you convert about 0.25, 0.3 will be falling sort of 4 seconds. So, if you are having low frequency components like you see there, the wind is even very low compared to the wave spectrum. Later on you will see in your hydrodynamics course, this is true for most of the sea states, you go all around the world, you know. So, having a fixed structure in this fashion, avoiding the peak energy area of most of the spectra will be better, because the excitation and the associated resonance will not happen, and that is the idea behind. This corresponds to about 4 seconds, this corresponds to about 14-16 seconds, here about 20 no. So, this is about 5 seconds, this is about 16 seconds. So, you can see there it is an interesting idea that the people have derived or devised a system in that fashion. Something similar given in period, fixed versus compliant. So, the most of the energy content of the wave will be between, in fact, about 10 seconds to 16 seconds, potentially very large energy magnitude, whereas the fixed platforms we keep it in this side, the compliant tower or floating systems go into the other side. What we will try to do is, we have few more slides and then we will try to complete today itself. So, basically the idea of shallow water, deep water, these numbers are not very strict. 500 meter could be a deep water several decades back. Today 500 meters is not as bad as what they were thinking about 20-30 years back. It is becoming very much shallow water. So, it is a gradually changing trend, you know. Today we think 1000 meter could be difficult to do a project, but prove to be easy afterwards. Ultra deep water, most of the time we go for a floating and moored systems. Deeper water, still talk about floating systems or semi floating systems or some very large fixed structures like 675. If you go into net, search for largest deepest jacket, you will find one of them installed in 675. Most of the shallow water conventionally jackets, but then some of the recent projects prove that even in 300 meter water depth, people are using FPSOs, as the reason that I am trying to explain is very good, because economical, relocatable, and you know, very cheap. We will just focus on what exactly the idea we were discussing few minutes back about the load transfer for fixed structures, so that tomorrow we can move on to a new chapter. So, you see the first one, conventionally individual pile. You might see this type of construction when you go to coastal areas or even land. You drive several piles and fix up a superstructure on top, something like this. You have a cylinder system, 1 or 2 or 3 depends on the load carrying capacity, and basically you see this is the starting point of a piled structure. You have a tubular or other forms of piles is driven into the ground and bring and install superstructure. But one of the problem here, you see here the superstructure is brought from somewhere, because it is prefabricated, isn't it, because this platform is installed in the middle of the ocean. Now, to fabricate this in that location becomes a bigger worry. So, normally what is done is you prefabricate mostly not concrete, mostly steel structure, so that you can transport easily without much trouble and put it on top. So, if you see there in this picture, the spacing of these supports have to be pre-arranged. Now, installation of this pile at a pre-destined distances between each of them have to be very accurate. If you install by half a meter incorrectly, because this is already fabricated, isn't it, when you bring it and install on top, it may not match, the support points may not match. So, what will need to be done? You either need to change the location of the pile, which proves to be very difficult, number 1, or you have to change the superstructure. So, how do we avoid this? Basically a simple idea that you provide a template for pile driving. I think most of you might have seen the templates for driving nails, driving other forms of structures. just make a opening on the seabed with a template and you drive the piles at that predetermined location. So that this can be easily installed to a prefixed dimension. So that is the idea behind. You see the next picture, instead of making a template only at the seabed, because again the piles could prove to be opening at the top because of the wave load. So you have a template which is just in dark blue color, made of a steel frame only for driving the piles. So the idea behind the method of called the jacket design is nothing but a simple template only for driving the pile. Once you do this system, the pile need not be very large, because it is fully braced system, the pile is going through a frame. So while doing this, what has happened is the pile has gone through without any problem at a predetermined spacing which was designed to be required by the superstructure. Number 2, the pile has become smaller because it is fully braced connection. So the slenderness ratio of this and this could potentially be different. So that is why sometimes we call it template type of structure, sometimes call it jacket type of structure. So you see here the load transfer here primarily bending, mostly little bit of axial transfer happens, whereas here primarily axial, because you are trying to decouple the horizontal loads as axial loads on the columns, because it is a fully braced frame and more stronger. And basically how do we prefabricate this so called a template? We have to bring it before we bring the superstructure. So that means that is exactly we are going to learn in this this course. How do we prefabricate, how do we transport, how do we install, and then drive the piles and then install the superstructure. So the various activities are involved. Now you see here, while doing so, you could see that this load transfer mechanism, instead of vertical columns, widened column base to reduce the load. If you imagine, if you make it vertical, the load on this will be smaller or larger? It will be larger, because the base is smaller. We can easily do a simple hand calculation. The horizontal load multiplied by the height or the center of load will give you the moment or overturning moment, divided by the spacing or the bed or the seabed will give you the reaction. Very simple calculation. So the larger the width at the base, you will find that smaller the load transfer to the soil and the foundation. So basically that is the idea behind. On several cases, you see these 3 pictures, how people have been thinking that you have a template at the bottom, template at the top, which controls the spacing. Then instead of that, because holding these 2 things together will become difficult, isn't it? How do you do it? Somebody have to hold the top and bottom without dislocation during pile driving. So in order to achieve that, you make a steel truss, just weld a few members. It becomes a simple template which happily anybody can drive the pile. And you see the last one is just a manipulation of this to reduce the pile load, because I wanted the base to be bigger. I think it is a simple idea transfer from one concept to other. And the last one you can see there, when you see this picture, you install this pile through the leg, the pile and the column is duplicated, isn't it? Whereas you go here, the column is separated from pile, so that what you can see here, the wastage of material inside the full length of the column is avoided. Only difference is the pile has to be installed through a underwater system. So this is called a skirt pile, this is called a main pile. That is the difference. The pile through leg is called main pile, whereas the pile is driven through additional skirt or additional sleeve is called a skirt leg pile. It is just a difference. You got both of them vertical inclined. The last one we made the pile to be vertical, which facilitate the installation quite a great extent. So you can see from the last 2 pictures how thinking was put together constantly to improve and reduce the cost and reduce the risk in offshore installation. So basically this jacket design is not something new, it has been there for several years and decades, and in fact it has become a very simple projects nowadays for jacket design. So, we will look at the next chapter tomorrow, I think. Any questions? So, I think today, yesterday and today we have seen what is the necessity of offshore structure. I think most of you have understood, no? And basically various systems available, and the one that we are going to focus for this project, for this particular subject is fixture structures, and under fixture structure typically a template which is used as a pile driving facility. Actually, the jacket is not something that is built for other purpose, it is only for driving the pile at the predetermined spacing, and number 2 is increase the base, number 3 reduce the slenderness because you got a braced system. And basically we will see the developments, how we can achieve these pictures. When you see here, how do we achieve this 3 stages: fabrication of jacket, fabrication of superstructure, pile driving, and then jacket should be transported from land, because everything is fabricated on land, no. So, we will see, maybe tomorrow we will go through one sequence of transportation from land and to the final location, maybe 1 or 2 classes is required, then after that we will go to the design. Okay.